Alright, so welcome back, and this is the Chipmaster, and in this class we're going to talk about discuss in this class the Apple A1989, the Type C boost process, the boost sequence, and we're going to touch a little bit on the Type C architecture and so forth and other things. Alright, so here I first have the schematic of the Apple motherboard, which is the A1989. I also have the screenshot that I'm gonna explain each step. So if I'm explaining a particular part or component, I can use the screenshot here to locate a specific component in conjunction with the board view. Alright, so this is the board view, and this is the A1989 board view, as you can see, and I'm going to use this as a reference, as a guide. So this is a demo class, so I'll not go all the way. Right, this class will take up to about 8 classes, each is 1 hour, and I'll only do 1 hour class, which is a demo. Okay, so first let's look at the Type C architecture, right? Because as you know, these laptops, Apple machines use this Type C, right? And this is the Type C connection here. This is for 2 parts, A and B, and you have another part, another section over here, another connector, sorry, over here, right here, which is connected to this connection here. Right, so this is used to control 2 USB-C ports, so it's a total of 4 ports that is on this motherboard. Alright, and this is the screenshot of the front side and the back side of the motherboard. Right, and I'll explain each step with help of this scan the image and along with the board view. Alright, so the Type C architecture that I've typed out here, which is the new technology that is implemented with the Type C. Alright, as we know, the Type C can have multiple voltages coming in and release and sending it to the motherboard, also with other signals such as USB signals, display signals, and so forth. Okay, so we're going to look at them. Okay, alright, so this is the USB Type C interface, this section, this image here. As you can see, we have 2 sides, we have A and we have B side, right? And this is the male. As you can see, the connections is inside with this plastic holder here. So this is a male connection, and the outer shell, which is the casing or the ground section, and inside is the A and the other side is the B side. Alright, so it says no many electronic products use Type C interfaces for charging. It also supports fast charging, and the adapter using this door, right, or a gateway, and it can support a variety of voltages, right, such as 5 volts, 9 volts, 12 volts, 15 volts, and 20 volts output. This should be 15, not S. Alright, this is, and its output is optional. However, devices that uses the Type C to connect have a logic chip that is responsible for managing the interface, right? So the chip is mainly responsible for communicating with the adapter, right? The protocol conversion, decoding, and conversion of other signals such as display signals, right? And first there are, and so this is basically what the Type C interface is, right? So it allows the motherboard to select its own voltages ranging between 5 to 20 volts depending on the type of devices that is plugging in, right? So for a cell phone, it's normally between 5 to 9 volts, right? And so it's normally 5 to 9 volts, and if it's a laptop, it will be like 15 to 20 volts, right? And as you can see here, we have here the pinout architecture of a Type C interface. As you can see, so we have A and we have B, right? So the A side, and this is the B side. So as you can see, we have TX1 plus, TX1 negative, right? We have V bus, we have CC1, we have D plus, we have D minus, we have SBU1, we have V bus, we have RX2 negative, and we have RX2 positive, right? And ground. Alright, and the B side, which is the reverse. So as you can see here, looking at this, you can see that this is the breakdown of the Type C architecture, or the Type C connector on a whole. So we have TX plus, TX1 minus, and this is transmitting signal. These are used to transfer display signals, or if you want another way, you can use type C to expand. So you'll see some other laptops have a regular DC in jack and it has a type C interface. That type C interface is for most likely for expansion, right? As I said before, it supports fast charge, so you can plug your phone into the laptop and get fast charging from the laptop, which you would not get from a typical USB 2.0 or USB 3.0 port, because a typical USB 3.0 or USB 2.0 port uses about 500 milliamp of current, and that's not going to charge the phone as fast as it should be. But you have some motherboards now with dedicated chips on the motherboard to support fast charging, right? But you'll normally find it on the type C machines, right? So this is the architecture. So this is a differential interface bus right here. So TX1 plus, TX minus, TX1 minus, and this is used to transfer display signals, LAN signals, HDMI signals. Other signals can pass through this differential interface, right? We have VBus, which is the main power supply input, right? The main power supply output, sorry, and it can output designated voltage to the VBus, right? And we have CC1, which is CC stands for configuration channel. This is the communication bus between the charger and the motherboard, right? And the logic chip that is responsible for talking to the charger so it can send out its necessary voltages, right? We have USB 2.0 here, which is D plus, D minus, right? And USB 3.0 is also supported. So D plus, D minus, as you can see, the reverse, because it can plug in either side, so it is symmetrical. So the two ends are identical, A and B, right? Two sides are symmetrical. And this is SBU1. This is normally used for auxiliary, right, which is rarely used. And as you can see, it's the reverse, RX2 minus and RX2 plus, and then we have ground. So this is the A and B side. So as you can see on the image, so we have this side can be A or it can either be B, because it can plug in either way, right? So the CC, which stands for configuration channel, type C, right? Configuration channel, which is the bus communication, right? So when the adapter is inserted, this is the process of how the type C communication works with the adapter and the device, right? Whether it's a phone or a motherboard or a laptop, sorry, right? So when the adapter is inserted into the notebook, it will tell the notebook how many voltages and the corresponding currents the adapter can provide, right? So after learning the power supply capability of the adapter, the notebook selects the most suitable power supply method from and sends a message to the adapter request packet, right? This request packet is where the data is going to pass through, which is normally through this line, the CC1. This is where this is where the communication is taking place. When it is plugged in at the first time on the motherboard, it is going to communicate through the CC1 line, right? And makes that request through the request packet. The adapter sends an accept command. After evaluating its capabilities according to the notebook selection, the adapter performs internal voltage conversions and sends a power ready packet to the notebook. Alright, the adapter applies the negotiated new power supply to VBus voltage, right? So this is a conversion, and it decodes the information through that chip, that logic chip, and it is sent to the and it is sent through this line and then through the VBus to provide the designated voltage and current, right? So I have screenshotted here at screen from my oscilloscope of the communication bus, the CC bus, how it is, the waveform is displayed on the oscilloscope when the CC bus is communicating, right? So you can see I have 1 volts per division, and I have my time base set at 20 microseconds, right? And I've captured the CC bus on this motherboard, which is the A1989, and you can see that the communication, the different communications, right? So the CC bus waveform, when the adapter is communicating with the motherboard. So as you can see, this is the VBus, which is the power supply, and this is the CC configuration channel, which is the data line, which is going to talk to the charger. So as first, 5 volts is generated from the USB type C. Remember, the default voltage that comes out of any type C is 5 volts. So 5 volts is output first, right? And then After we have set this to 1 volts per division, and my channel 2 is set to 5 volts per division because default is 5 volts, so this is 5 volts, see, 5, and this is 1 volts per division, and my time base is set to 100 milliseconds. So while the voltage for 5 volts is outputted first, during that first 3 communication, right, so that's roughly 1, 150, 200, 150, 300 milliseconds, then it will start to boost the voltage to 20 volts. So that's 5, 10, 15, right? So 5, 10, 15 volts for the V-bus. As you can see, this is V-bus is for a small Chromebook, right? This is not for the Apple, right? Because the Apple is boosted to 20 volts. As you can see, after the first 3 communication, right, then the adapter will start to boost during this period. So from here to here, that's roughly 200 milliseconds, 210 milliseconds, and then it will boost, and then its final communication to confirm the packet, the packet that is confirmed, which is a power ready signal. As you can see, power ready, right? And then it is outputting its correct voltages of 15 volts, which is sent to the motherboard, right? So that's basically how the type C communication is done on a laptop, right? And I've basically written out the steps here of how the motherboard is communicating with the adapter in order for it to send its correct designated voltage and current right through the CC line. So if any fault on this line, then it will stop at 5 volts and it will not boost to its designated voltage, because there's a fault on the CC bus line, which is here, right? So if this is our fault on that line, then there is no voltage boost, so it's stuck at 5 volts, hence the device won't power on or charge. Alright, so we're going to take a look back at this, the official documentation and what I'm intending to teach. And this is the A1989 motherboard. As I said before, I have the screenshot here, and I also have the schematic and the board view. Alright, so this is the Apple A1989, and this uses 4 type C bus interface, 4 type C connection. Alright, so here is a connection on one side. This manages 2 connector, and on this side we also have another which is managing another 2, which is a total of 4 connections on this motherboard. And we're going to use this as our reference. Alright, so first I'm going to get the diagram designer. So I'm going to steps it out. I'm going to give the steps while I analyze the circuit. And I'm going to do it in a pictorial form so it's easier for reference when using. Alright, so first I'm going to go to this connector here. As you can see, this is the connector. This is the DC in. Our V-bus connection is through these pins. Alright, so I'm first going to go to the schematic, to the board view, and I'm going to look at the connector, and it is J3300, or we can say J3300. Alright, so we go to the schematic and we look for J3300, right? And we have found it. My machine is not making correctly today. Why? Anyway, alright, so this is the J3300 connector, as you can see here. So we have J3300, and we have all these pinouts and various signals and stuff going out and into this connector. Alright, so as you can see on this side we have the USB-C sections. For example, we have USB-C XA. So XA means this is the A side, right? So we have USB-C XA underscore USB underscore DBG underscore BOT underscore N. This basically means that this is a debug. See, DBG stands for debug, and it's the bottom side and it's a negative. So USB is, this is the X, this is the A side, right? And over here should be the B side. Let's see. Alright, here is the B side. So we have USB-C XBCC 2 underscore CONN. This is a connection for the USB-CC communication line on the B side, right? And we have USB XA CC communication 1, and this is for the B communication configuration channel CC2, and we have the A side. All right, so this is our A side USB. This side is for the USB 2.0. Let me get my, yes, so this side is for the USB 2.0. as you can see, so USB-C, R2D-CRP and 2D-CRN, right? And this is a positive, a set of negative, and this is the USB, and it is sent to the Thunderbolt, but this is actually the USB connection, right? We have CC2, which is the CC bus 2 connection for the A side, right? So all of this is for the A side, right? As you can see, we have a set of Zener diodes here, or we can call it a regulated diode, which will normally clamp the voltages if any over current or any interference that exceed the data of the voltage to pass through, then it will clamp it. This is for protection. As you can know, as you see, it is on the data lines, and these are used to stabilize the voltage or the data that is passed through, and these voltage have a threshold value of when it is over the limit or the threshold, then it will stabilize it. As you can see, the negative side, the positive side of the diode is connected to ground. So what will happen is that if there's a overcurrent or any once an overcurrent action occurs on this line, then it will reverse, it will do a reverse conduction, and then it will stabilize the voltage at, let's say, for example, 5 volts, and 5 volts will be here for stabilization. So this is called a clamping technique of a diode. Alright, this is not a diode class, so I don't go so deep into the diode section, but you get what I'm trying to say right here. Alright, and this is for the USB bus section, right? And I'll go over to the next side, and it's the same. Alright, see the Zener diodes, or the clamping of the diodes. Alright, this is debug, this is for diagnostic purpose only, right? Top, this is the top, right? And over here we have the bottom side. See, USB-C underscore XA, this is the bottom side for the A side, right? On the bottom side, on the top side for the A side. So this is the top, and this is the bottom side. So remember, it is symmetrical, so it can plug in either way. So you have to have an A and B, a top and a bottom, right? And over here we have the B side. We have the USB-C, which is the data line to communicate with the charger to output the voltages, right? This is the auxiliary section, SBU1 auxiliary, and we have the USB 2.0 section here, right? All of this USB section here, and this is USB. Oh, I forgot one thing. So this is the USB section, the auxiliary. This is USB-C, right, positive and negative, and this is the differential signal, TX1. So this is T, right, TX1 positive, and this is TX, right, 1 negative. So that was my mistake. I forgot that there is a differential signal line, right, which is on the USB architecture here for this part. So this is the section that is just highlighted, right, negative and positive, and this is the USB section, USB 2.0, USB 3.0 section, right? So this is the TX, the differential signal, right, and this is used to transfer like the display signals, or for expansion purposes, such as you can expand your LAN, you can expand your VGA, you can expand your HDMI. All that signal is passed through this section here, right? And this is the section, and that is why it has all these diodes, because this is high frequency passing through these two lines, right? And it has to have the Zener diodes to clamp it for stabilization and protection, for ESD also, electrostatic discharge, primarily for electrostatic discharge. All right, now let's look for the power supply, the V bus, and it is up here, as you can see. So we have V power, right? So as you can see, we have power. This is the VBus section, right? And if you trace it back, we go to this side, and then we have this, we have the stabilization of the diodes here, very important, right? So as you can see, the positive side of the diode is connected to the ground. So if you get the data sheet for this Zener diode, then it will see the reverse conduction voltage value, right? This should be a maximum of 20 volts. It's difficult to draw with the mouse, right? This should be a conversion of 20 volts. So if 20 volts exceed, if the voltage of this line exceeds 20 volts, this voltage, this diode will do a reverse conduction, and it will keep it stable at 20 volts, and this is called a stabilization of a diode, or clamping of a diode, right? As you can see, so we have pp20 volts underscore USBC underscore XB underscore VBus. So this is for the B side, right? XB, and over here should be for the A side. Let's see, the A side, let me see, A 20 volt XB, and the A side is on the other board. It's on the other side, other one, which is here. Let's go to the right, and over here it's the other side. We're going to work with the B side. Alright, so I'm going to work with the B side for reference. Alright, XAV bus, sorry, here's the A side. So this is the A side, pp20 volts underscore USBC underscore XA underscore VBus, and up here is the B side. So B and A. I'm just going to work with the B side, it doesn't really matter. Alright, so this voltage of 5 volts by default. Remember, each time you plug in a type C device, USB, the charger, it's normally 5 volts. So before the boost, it will have 5 volts coming in. Alright, and that 5 volts is going to power some logic chips. Alright, so as you can see, we have pp20 volts underscore USBC underscore XB underscore VBus, and it's renamed. Well, it's not renamed, it's the same name. Don't see any changes, so we can move on. Alright, coming through a fuse here. So after coming through the 6 amp fuse of 32 volts, right, it becomes pp20 volts underscore USBC underscore XB underscore VBus underscore F. Right, so it's changed its name. Let's look for the whereabouts of this. Continue to look for the whereabouts. Alright, there we go, and it is coming to this section here, which is the USB, and this is the isolation and protection section. As you can see, we have 2 N-channel MOSFET integrated in one package. Alright, and it is being controlled by this chip, and it is called CD3215A, and it is U3200. And let's look at that at the board view. So we have U3200, and it's okay, and this is the logic USB-C chip communication chip. As you can see, it's a BGA package, right, and it's right beside it. Okay, so here is it. So it's this chip, right? So it's clear enough. So not clear enough. All right, so it's CD3215C00Z, right? This C00Z, this last part here indicates that there is a software. It uses a software. All right, let me get my pointer fix so I can highlight. Alright, so this chip uses a software, and this chip is it reads an EEPROM chip. So this is the software version, C00Z, right? And flashing or swapping these chips randomly, you have to be careful, can cause no 20 volts boost. So if you put a 00B here, it will not work, because the software which it's read, it's different. So you'll have to reflash the BIOS for this chip in order for it to maintain its 20 volts, right? Otherwise it will just stuck at 5 volts, and you wonder what's happening. So you cannot randomly change these chips, right? They are different in terms of the software version. Oh, sorry, I forgot that I'm using a different software, right? In terms of the software version, so you must be careful. So this is the CD3215000Z chip, and this is the logic chip for communicating with the adapter when you insert the adapter on the connection here. So the 5 volts is gonna come to here. Let's go back to the schematic, right? And let's go back. Right, so this is pp20 volts underscore USBC, right, underscore USBC. Where am I? Sorry, I was looking at something. Right, so it's pp20 volts underscore USBC underscore X bus, and it's coming after passing through the fuse. Right, so the fuse is here, and that's F3001. Right, so F3001. So let's take a look at that on board view. F3001. Okay, and the fuse is right beside it here. Let's go over to the board view, and here's the fuse. All right, this is the fuse. F3001. So 5 volts through this, 5 volts coming through, and this is the MOSFET. All right, the MOSFET is here. Right, yes. So here is the MOSFET, and this is the MOSFET Q3200. Right, and that's the MOSFET here, Q3200. So let's look at the board view. Right, see, Q3200. Right, so this is a dual MOSFET, right, 2 MOSFETs inside. So pp20 volts underscore USBC comes to the source pin, as you can see, S2, right, comes to the source pin of Q3200, right, and it is controlled, the gate, as you can see, is controlled by this chip, which is UPC underscore XP underscore gate 2, and it is connected to the A9 pin. See, high voltage, high the HV, high drive voltage, right, and it is going to turn on this gate. Normally I measured when I tested, this voltage is roughly 6 volts, right, have to be, because it's an n-channel MOSFET, because this is 5 volts coming in it, right, and 5 volts is coming to the source, right, 5 volts is coming to the source, right, and the gate is 6 volts. So when the voltage at the gate, right, is greater than the voltage at the source, then it will do a full conduction, right? So 5 volts will pass through here and stop here. As you can see, the orientation of the body diode, so this voltage cannot be dropped, because this body diode has a voltage of about 0.75 volts, so that will drop it to about 4.7 volts, and you don't want that, right? So 4.7 volts will come here, and that will cause a problem. So you must have full 6 volts conduction here to get the full 5 voltage, so that this voltage will conduct after going through the second MOSFET, and the second MOSFET is controlled by UPC underscore XB underscore gate 1, right, and it is coming right here, which is HV underscore gate 1. When I measure this voltage, is roughly 10 volts. Why? Because of the boost. Remember, when the 5 volts comes into this chips, so this 20 volts, this 5 volts come here, it is coming to this pin V bus, right? V bus is 5 volts. You should check out this capacitor C3201. This capacitor is very important. Removing this capacitor can cause unstable voltage and can cause power down, right? And this voltage, this capacitor is it's C3201, right? C3201. All right, good. So C3201 is right here, and here it is. So this voltage, you should measure 5 volts here, right? As I said before, this capacitor is very important. If you remove this capacitor, then it can cause the voltage to be fluctuated and can cause damage to this chip and can cause power down. So if this is shorted, please replace it back with the correct value capacitor, right? As you can see, it's a 1 microfarad 35 volts capacitor, right? And this 5 volts coming to the V bus pin. When this chip get this 5 volts, right, automatically it will use the 6 volts. Remember, there's a diode that's this chip has a diode that's inside, right, a diode that's inside. It's difficult to draw with the mouse, you get what I mean, and it will drive upper gate 2 first and conduct 6 volts full conduction. This 5 volts is going to add to the boost of the diode, right? The diode, as you can, you know, right, the diode 5 volts is going to be added because it's a boost, and this will add it to 10 volts, and 10 volts which is coming to this gate here, and you get full conduction, and it produce PPDC in G3_H, right? And this is also 5 volts. Remember, we are talking about before the boost, right? So PPDC in G3H is 5 volts, right? After this MOSFET it gets its full working conditions of 6 volts and 10 volts, then it will conduct that 5 volts and send to the charging chip, as you know from the typical classic MacBook motherboard. And this 5 volt is sent to the DC in to the charging chip. So let me clear this page here. All right, so this PPDC in is going to send to our charging chip, and it goes to many places. So let's copy and move down step by step. All right, here is our charging page, our charging chip section, charger section. Let's go to the bottom. As you can see, right, BP bus supply and battery charger, right? So this is our charging chip U7000, as you can see here. All right, ISL 9240, and this is also a BJ package, as you can see, right? And we also have another MOSFET here. This is our isolation, and this is the boost, the 4-switch buck boost regulator circuit. So it can act as a buck and it can act as a boost. As you can see, there's a coil which is in the dead center in the middle here, right? And it's not drawn, right? So first let me just sketch out this diagram first before I forget. So let me go for the connection. Alright, so this is our DC in jack. Let me get my fast stone capture here. I want to cut this image. Alright, so this is the B side. Alright, so let me extend my canvas here. Objects, page properties, the canvas to about 500. Alright, let me make this a smaller size. Alright, so you know our 5 volts is from here, and also we need to have here our CC configuration line. So let me copy let's go back to this one, so I can go back to my main page. Alright, section, yeah, here. So before going to the fuse, it's called PP20 volts. Oops, sorry. Alright, so PP20 volts. Let me copy this fuse. Alright. Alright, so after passing through the fuse, it has been renamed to 20 volts underscore USB underscore CF. Alright, and it is sent to our U3200 and U3200, which is our BJ chip, which is here. Let me see if I can get a picture. Oh, sorry. Should be at the top. Oh, good. I'm going to put this in a box so I can send to back. Alright, this is our USB-C chip, logic power delivery chip, communication chip, or we can call it the CC configuration protocol chip, and that's going to go here. Right, let's put a dot there. Good. Alright, so the 5 volts that's 5 volts coming in, and it's gonna control the gate of our MOSFET, which is Q3200. I'm just gonna draw 2 MOSFETs. Right, and it's being controlled by Alright, and this is after the conversion, so I'm just gonna get the gates name. Alright, for schematic, and the gates name we have USBC underscore XP gate 2. Hey? I keep forgetting. Hey. Okay. Right. Okay. I need to get this one. I see. Alright, so I'm gonna change the font size, 2-digit size to 49876. There we go. Alright. next one. Put the size small. We're gonna rotate. Alright, so we have our gate voltage, and this is Q3200. Alright, so Q3200, and then it produces our a MOSFET. Oh, I see. I keep forgetting. Yes. All right. Alright, so we have the two MOSFETs, and these are now called PPDC in. G3 underscore PPDC underscore G3 H, and this is sent to our charging circuit. So let's move on to our charging section now. Alright, so this is the charging section, and this is our charging chip, which is a BJ package. As I said before, it's called ISL 9240, and let's look for this on the actual appearance on this. So it's U7000. Oops, need to type U7000. U7000. Yeah. Alright, so here it is. It's a BJ package, as you can see, and this is a glass chip, I believe, and this is very easy to break if you hold it too hard with the tweezers when desoldering or soldering. So you have to be careful with this chip. So U7000's location is on the next side of the board, so I'll have to zoom out and go up here. So U7000, oh, here is it, and U7000 is right here. So as you can see, it's a glass chip, right? And when soldering this chip, you have to be very careful. As you can see, we have some capacitors here and resistors for 5-volt linear output, which is going to power the internal logic inside and to provide boost for the 2-4 switch buck and boost MOSFETs, which is equivalent to produce our common point voltage, which is the PP bus G3H, right? And as you can see, this is the charging chip from this angle, right? And it's called U7000. Yeah, here it is. So U7000 right here. Alright, so this chip has a set of working conditions, as you know, right? So the PPDC in from USBC source comes in to this current sensing resistor. This is the adapter current sensing resistor, which has a 0.1 voltage drop on both sides, as you can see, right? 0.01, and a path before is coming through here, so PPDC in, as you can see, right? Another path is coming to this charging chip through this resistor voltage divider, and it is going to create charger underscore AUX underscore detect, which is the adapter detection signal, right? And this is coming to the D3 pin of the charging chip, right? Let's go back, and another path after coming to the current sensing resistor is coming to here, and it is coming to the charging chip, and this is P in. So P in is the main power supply pin for this charging chip. P in. Alright, so P in is the main power supply chip. When it gets the P in voltage, alright, this is 5 volts, remember. So 5 volts coming here. Anybody can tell me what's the next step? It will produce VDDP, which is the linear charge VDDP through this resistor, acting as a current sensing to power VDDA, and this is the analog section of the chip. So there are two sets of box chip. There are no data sheet for this chip. There are two sets of chip which is responsible for the boosting of the voltage from 5 volts to 20 volts, and it's going to power these two logic. One is analog and one is digital. So this P-in chip is going to power the main chip itself, and then it's going to produce a internally through an OR gate, normally through an inverter, and then it's going to produce 5 volts, and it's going to come from here. So VDDP is going to produce the voltage to power VDDA. Okay, so please bear that in mind. Alright, so this is our charging chip. So our charging chip P in VDDA. When VDDP and VDDA is powered, the next step is that these MOSFETs, as you can see, we have a set of dual MOSFETs here. So we have Q7030 and we have Q7040. These two chips is responsible for boosting and bucking. So at this time it's 5 volts coming here. Alright, 5 volts coming to this, right, the drain pin, and it is going to stop here. So it needs to be cut. So this MOSFET, right, G1 pin needs to be conducted, and this is an N channel MOSFET, as you can see, right? So this voltage needs to be higher than this voltage at its source. So its source is 0 volts at the time. So within 4.5 volts or more, which is the threshold, 4.5 volts or more coming to this gate, then it will do a full conduction, right? And it will come here. So what will happen is that this charging chip, right, the charging chip, right, so the charging chip through gate 1, as you can see, which is telling us that there's a switch, right, a diode that's inside, just a switch node through, will come through to the gate and conduct here, right? I've measured here, and I've got hold on, I'm trying to clear this here. Right, so this voltage, minimum voltage, as you can see, is roughly well, it will boost it to up to 20 volts because there's an internal pump, a charge pump that's inside, right, that will boost this voltage to 20 volts up to 25 volts, right? Let me see if I find the waveform. I think I've screenshotted a waveform. Alright, so I have the waveform here, as you can see, Q30 and Q7040, right? And this is Q30, right, Q30, and we have Q7040, a waveform that I have saved from my oscilloscope, right? And it's going to open a few. So the voltage here should be, when I tested it, it was roughly, where is it? Okay, so right, so it wasn't 20 volts. So the channel 2, which is the red one, which is 10 volts up to 15 volts coming to the gate, right? And this is the Q7040, sorry, and this one is channel 1, which is the Q7040, and that's 2 volts per division, 2, 4, right, 6. So as you can see, this voltage on this gate has a higher voltage than of this one because now it's going into the boost mode. So this voltage at this gate is 20 volts, 510. So let's go 5, so it's red, the channel 1, channel 2 is the red channel, which is 5 volts per division, 5, 10, 15 volts peak, but after boost it's 5, 10, 11 to 12 volts. So 12 volts coming here, and then now it's going into the boost mode. So even before the actual 20 volts is boosted, the voltage here after measuring at this fuse should be 20 volts. Before the boost and after the boost, 20 volts should be here all times. So if a case happens when you're repairing this motherboard and it is stuck at 5 volts, then you need to check the working conditions. Right, so 20 volts is here at all times, regardless if it is in boost before or after the 5 volts has been boosted. Alright, so let me just clear here. Let's just delete them. Alright, so this voltage at the gate is 15 volts max, right? 15 volts here for conduction, right? As you can see with the waveform here, I've used at my oscilloscope, right? So this is Q7030 and Q7040 gates, the two gates at the same time conduction, right? And this is going to produce, I'm not going to explain in depth because this is a demo video. Have this, the information is here. I have in how this 12 volts is produced. I won't go in depth because it's a demo video. I'll only explain this in the paid class, and I'll explain how this boosts from 5 and you get 20 volts here, regardless if it's before or after the voltage has been boosted from 5 to 20 volts. Right, so this condition must be met first in order for this action to take place. Right, so P in, then VDD-P for VDD-A, and then it will produce what? Q, gate Q1 and gate Q2 for the conduction of these three gates rather, right? 4 gates, sorry, 1, 2, 3, 4, right? So these gates, there are 2 MOSFETs, a total of 4, so 2 on this side and 2 on this side, right? And they must be conducted, right? And they conduct, as I said, in a rotation conduction, and then to produce the boost of 20 volts. Alright, so after the boost of 20 volts is produced here, we have another pin that we should take care, which is the P bus power. So after this voltage of 20 volts is sorry, not 20 volts, it's 12 volts. My mistake, gentle people. This is not 20 volts, it's 12 volts, 12.8 volts after the boost, right? PP bus G3 high is 12 volts, sorry, not 20 volts, 12.8 volts. Alright, so this is 12.8 volts before or after the boost, regardless if the adapter is at 5 volts or 20 volts. Alright, PP bus G3 state high is 12 volts, so you should measure 12 volts here before or after the boost, right? And it is going to power the system. Right, this is 12 volts, that's my mistake, not 20 volts. Right, it should be 12 volts. So after this 12 volts is generated, this charging chip needs to detect that the voltage is already created and generated and is okay, and it is coming to this pin, which is called P bus underscore power. So let's see where this is coming. Alright, so we trace it, so P bus underscore power, and that's going to here, which is coming to P bat underscore charge underscore regulator. So let's copy this signal and paste. Alright, so it's there. Searching. Alright, found 2, found 3. Alright, so that one. So here it is, see? And it's coming from here. So it is coming from the same section I'm coming from. So PPV bat underscore G3 underscore charge underscore reg, which is a charge regulator, is going to tell the charger that it's the command point, right, which is generated and it's okay, right? Then it can move to the next step, and we have another detection signal here, which is the P bus, which is the power, right? And it is also monitoring the output current of our PP bus, right? So the A3 pin, which is here, and is coming to the current sensing resistor, and this information is going to be sent to the T2 chip through the M1 pin. This is for our battery monitoring current signal, right? Battery monitor current signal, and this is the P bus, which is connected to here, right, through this current sensing resistor and through these other sensing resistor. Very important. Okay, right. So this resistor is responsible for monitoring the current. So this P bus, if there's any fault with these resistors, right, then we won't have 12 volts here, right? The charging chip will go in protection mode and the 12 volts will not be produced. So we need to check the working conditions and check these resistors, right? So that P bus, which is an input pin coming into the charger, right, and this is also another input pin coming into the charging chip, right, and then that current will be monitored, right, and it will be sent, and it is monitoring the adapter current information through P in pin and CS in pin, right, and that information is also going to send to the SMC, this MA on. So all this information is going to pass through MA on and B on, one for the adapter and one for the battery. So A stands for adapter and B stands for battery. So the battery current sensing charge current sensing signal is here, charger underscore current sense right, positive, and resistance positive and negative. So those two signals are sent to here. See, CSP and CSOP and CSON, and that information is going to go to the battery. And the charger section, let me clear it, is a bit crowded. Alright, good. Remember, so the P in pin, which is the CS in pin, as you can see, is coming from the adapter. So see, charger CS current, right, negative, which is coming to the negative pin, and the positive to the positive pin. Those two information are multiplied 20 times inside of the charging chip, and it's going to be sent the voltage difference to the A on pin. Normally this is about 0.2 volts here, right, and this is for the battery. As you can see, the battery, which is CSP, and it's going to calculate it 20 times, and it's going to send here to B on, which is for battery, and that information is sent to the T2 chip. As you can see, out, right, out, these are going to the T2 chip for the T2 chip to monitor the output current of the system and the charge current and charge voltage, right. Now another pin, which is the cells pin, this is the battery calibration detection cell pin, right, and this is also connected to here. As you can see, 5 volts. So 5 volts is connected to here. So when the cells pin is connected to a voltage, right, the output voltage will be our common point voltage of 12 volts. So the cells pin is also going to tell the charging chip how many voltage to produce at this section. Alright, so this section here, which is called the cells pin, this is also the battery cells, as I said, calibration pin setting, and the common point output voltage setting, right. A lack of this voltage is if there's a fault here, if there's a fault with this resistor, we won't have 12 volts here either. Alright, 12 volts will be not generated for the PP bus G3 state high. So we need to make sure that we check this pin. There's no way to check because of BJ, so all we have to do is check this capacitor and this resistor, and we know that 5 volts is there, right. I'm going to stop here. I'm going to continue another time because of time. I have to work, and this is a demo video. I have to tomorrow I'll continue for the part 2 of this demo video. Okay, thanks for watching.